So irradiance is defined as the power per unit area, or in formula terms, I equals P over A. And I'll do a worked example of that along with outcome 3. That formula is true for any type of source, but if we look at it specifically from a point source, first of all, what do we mean by a point source? So a point source is a source where light is emitted evenly in all directions. So stars are actually quite good at that. They're roughly spherical, so they emit light equally in all directions. A small light bulb is a decent approximation of it as well. Bigger the light bulb, then you start to actually see the size of the filament inside, and then you find that it doesn't go equally in all directions. You've kind of got the physical dimensions of it. And certainly a light bulb with reflectors behind it, like you might find in a torch or a car headlamp, is not a good point source, because the reflector changes the direction, puts all the light into one direction, so you don't have it spreading out evenly in all directions. So first of all, that's our definition. And so if you've got your point source, and then you have measuring tape or meter stick, something like that. Or some way of measuring distance. And then you have a light sensor or something, a light meter. Measure the irradiance using the light meter for a range of different distances. Now, in theory, for a point source, because the light spreads out evenly in all directions, the area will be a sphere, and the surface area of a sphere goes with the radius squared. So the area on the bottom line of the I equals P over A will be proportional to the distance squared, because that will define a sphere where all the energy is spread over. So what we find when you collect this data for irradiance and distance is that if you plot a graph of I versus D, well, it decreases. It follows a curved shape, so you can't tell anything directly from that. But if you plot a graph of I versus 1 over D squared, then you get a straight line through the origin. Sorry, not a very good straight line, but and this shows, therefore, what we call an inverse square law for the irradiance versus distance. So that inverse square law can be written as I is equal to some constant K, which depends on the power of your light source, divided by distance squared. And the constant will vary in lots of different situations. Now, another way of thinking that, and the way this is more commonly used, although this is what appears in the formula sheet, is that your constant is equal to I times D squared. So if you compare the irradiance at two different distances, instead of having to work out the constant, we can simply say that I times D squared at one position is equal to I times D squared at a second position. And we'll see in a worked example that this is the way it's often used, even though it's a 1 in the box, I equals k over d squared, which actually appears in the formula sheet. So let's look at a worked example based on that. So for part A, we're told the area, and we're told the distance. We'll find we'll use that in a wee second. And we're told the irradiance is 0.01. Okay, the units of irradiance are watts per square metre power divided by area. The distance I'm going to call D1 is 3 metres, and I'm going to call that I1 to go with that as well. But for part A, we're going to use the first formula that we introduced, so I equals P over A. Substituting in 0.01 equals P over 2.5, and rearranging then we get P equals 0.025 watts. But more often than not, we're not dealing with the actual power of a light bulb, because that's quite complicated. I know we can measure you see light bulbs might say 60 watts, you can measure the power going into them, but working the power coming out from them is quite complicated. So more often than not, what we do is we say, well, we've now got a new distance, and what we do is we compare irradiance at different distances. So we're being asked the irradiance I2 at this different distance. And for that, we're going to use then this ID squared equals a constant. But in this form here, the I1 D1 squared equals I2 D2 squared. Now remember, this isn't given in the formula sheet. What appears is I equals k over d squared, so you need to be able to interpret that. So plugging in our numbers again. Now it's only the d that's squared, it's not the I, just to be clear on that. Make sure you do your substitution correctly. Don't forget to square, that's a common mistake. So you've done your substitution there, do your arithmetic. I'll simplify it a wee bit anyway. But rearranging that, so you get 0.01 times 9 divided by 2.25 is 0.04 watts per square metre. Now it's worthwhile just having a quick look at those values. When we were 3 metres away, it was 0.01. When we were 1.5 metres away, so half that distance, it was 0.04. So when you half the distance, right, the irradiance goes up by 4. Or the other way around, you think about it, if you double the distance, the irradiance goes down by 4. That's a good example of an inverse square law. So in the previous booklet, in the nuclear chapter, we met what's called the Rutherford model of the atom, probably the one that you've been familiar with, possibly even for primary school, but certainly at least first year. And that's the idea that you've got a nucleus with electrons in orbit around about it. And what Bohr discovered, so we're now going to look at the Bohr model of the atom, was that those electrons couldn't just be at any possible level or energy, but that they had specific energies, right, that they could be at, and that those energies were specific for each element. So in the Bohr model of the atom, electrons can only orbit the nucleus at certain energy levels which are unique to each element. Now you could imagine drawing them with your nucleus in the middle and the electron energies going round about them, so on. It's quite hard to draw it that way. But actually what they usually do is to kind of take a cut through that and draw just a set of straight lines to represent So the energy levels are drawn just showing the first energy level, so that might be that one there, and it's usually labelled as a 0. Sometimes with a W, sometimes with an E. And then the next one after that is E1, and then we kind of work our way out from the nucleus. So they're drawn like that. Now E0, E1 would be up there, E2 might be there, etc. And they do get closer together the higher you go. And most atoms have got quite a large number. We wouldn't be able to draw them all. And electrons can be excited for lower energies, which are always the ones to the bottom, to higher energies. Right, they can't exist in between, so you can't jump somewhere in between these energy levels. But they can be excited into these higher energy levels by adding energy. But when we tend to do that, as in most things in physics, they like to settle in lower energy states if they can. So you think about water likes to roll down hills, always getting to lowest gravitational energy. It will tend to fall back down. So electrons can be excited into higher energy levels by adding energy, or can lose energy to drop to lower energy levels. So for instance, you could go from E2 down to E1. And you can actually count how many transitions are possible. For instance, so if you start in E3, I could go to E2 or E1 or E0. And then if I went from E2, I could go to E1 to E0. If I went from E1, I could go to E0. So if you aren't being asked to count possible transitions, try and be methodical about it like that. So start at the top one, say where can I go, count how many that is, work to the next one down, and so on. Outcome 6, and outcome 6 says that the ionization level is the point at which an electron is just free of an atom. So that's what ionization means, you're releasing the electron from the atom. But it doesn't have any extra energy beyond that, it's just made it out and no more. So actual fact, that's defined as a 0. Because it has 0. It's defined as a 0 of potential energy. So comma, which means all the levels below are negative. Sorry, just running out of space here. So it's a bit like if you were doing a potential energy experiment, right, up in my physics lab in the 3rd floor, and I dropped something to the ground in my lab, I could say, well, that's the 0 of energy. But then if I dropped it down the stairs or out the window, it could go below that 0, which means the lab floors, biology floors and so on below would be considered to have negative potential energy. For potential energy, you can pick whatever is a convenient 0. The ground state is the lowest possible energy. Often labelled E0 or W0. And if we return back to the idea that we looked at in outcome 5, we talked about the electron gaining energy or losing energy. So when an electron drops to a lower energy level, it loses energy. But conservation of energy means that must go somewhere. So that is emitted in the form of a photon. So an electromagnetic photon could be visible light, okay, could be in other parts of the spectrum. In order for an electron to gain energy, to jump to a higher energy level, it can absorb a photon. And I'm going to group together 9 and 10. So we've got this idea that at both absorption or emission, that you've got an electron gaining or losing energy and either emitting or absorbing a photon. So in terms of our energy conservation, we can say the energy of the photon, E, is equal to the difference in the energy levels, E2 minus E1. But from the previous work we did on photons, we know it's HE is equal to HF for a photon. So HF is equal to E2 minus E1. So the energy of the photon, whether it's absorbed or emitted, right, HF is equal to the difference in the energy levels, E2 minus E1. Okay, and we'll look at a worked example of that over the page. So to solve these sorts of problems, you have to be given the energy levels involved. So in this example, you're given the energy levels for hydrogen, the ground state being the most negative, so minus 21.76, 10 to the minus 19 joules, and then all the other ones above that. And we're asked between which two energy levels would an electron transition lead to the emission of radiation of the highest frequency. Now what we were just saying a second ago was that that frequency is equal to the difference in the energy levels, or HF is equal to the difference in the energy levels. So the largest F will come from the largest change of energy levels. So our answer to part A is quite simply E4 to E0. You don't have to go to neighbouring energy levels, you can jump across many at one time. And then we can use that to work out the frequency of the radiation. So HF, in the formula sheet it says E2 minus E1, but you need to adapt that to the particular one you're dealing with. So E4 minus E0. And it always will be the upper one, take away the lower one, whether you're looking at emission or absorption. And now we can plug in all our values to work out F. So 6.63 times 10 to the minus 34 times F equals minus 0.864 times 10 to the minus 19. Remember we got 10 to the minus 19 as our photon energies quite often when we first met these in the photoelectric effect. And then it's minus minus. So you've got a negative in the formula, and the energy level you're dealing with is negative. So the difference when you do this calculation, you should always end up with a positive value. You can't have a negative frequency, you can't have a negative photon energy. Only potential energies can be negative. So you do that calculation watching your double minus, you end up with a positive value. Divide both sides by Planck's constant. And you'll get what looks like higher than visible, so it's probably an ultraviolet photon. The frequency of this radiation is 3.15 times 10 to the 15. Now, photons aren't the only way to excite electrons into upper energy levels. You can do it by heating, you can do it using radio waves, electromagnetic waves. But once an atom is excited, then, like we said, naturally it will tend to fall back down. So I'll stick with the example of heating. The electrons in the atoms are excited to higher energy levels. And they will fall back down naturally. Spontaneously is quite often what it's referred to. Emitting a unique set of photons for each element. These unique frequencies correspond to different colours. So if you can look at them through a spectrometer, so I just realised it should set frequencies. So a set of coloured lines on a dark background is produced. If you're looking at it through a spectrometer, if not, what you see are just the kind of colours that go with each element. If you think about the flame tests that you've done in chemistry, that's what you're seeing, just all the different colours blended together. But through a spectrometer you see them separated out. We get the exact sort of idea, same idea for an absorption spectrum, but with an absorption spectrum you need to start with a white light source. So if we shine white light at a cool gas, the photons which cause electrons to jump to higher energy levels will be absorbed, leaving a dark line against the full spectrum when viewed through a spectrometer. Because the exact same energies are involved though in emission and absorption, these dark lines will be at the same position, same frequency as the coloured lines of the emission spectrum. And lastly, these absorption lines were observed in the spectrum of sunlight and used to work out the chemical elements, or just elements, present in the upper layers of the sun. So the upper layers of the sun are relatively cool compared to the inner layers where the full spectrum is produced. And those cooler layers then will absorb some parts of that, and you can observe these lines. They're called Fraunhofer lines after the man that discovered them, and it was on his sort of theory as well that Bohr built his model of the atom. Not actually part of the course, but just out of curiosity, how do you get those continuous spectrums? So we've talked about line spectra. All this stuff about line spectra is when really we're talking about individual atoms, so you only really get it when you're dealing with low pressure gases. If you have atoms packed close together, then the electrons can jump to neighbouring atoms, and pretty much any energy level becomes possible, and therefore you can get photons either absorbed or emitted at any particular frequency. So in something like the filament of a light bulb, which we heat up, all those atoms are close together, and you can get electron transitions at any possible energy, so you get a continuous spectrum, and same in the centre of the sun.